Okay, in this video, in the last video, we were looking at different Calculus 1 topics that I wanted to make sure you kind of remembered from Calc 1. And we talked about the definition of an integral, areas between curves, areas under curves, things like that. In this video, a couple of tricks for integration that you should have seen. U substitution and integration by parts. And then we might, based on time, look at a few other topics, or I'll break that up into a third video. But all of you know the basics of integration, and these are kind of the first two basic tricks you learn. So just really quickly, suppose I have this, the integral of x times the square root of 25 minus x squared dx. And we understand right away there is a problem here, because I have a radical with an x inside of it and an x on the outside. And as far as tricks go, much like with differentiation in this class, with integration, we're going to have a bunch of tricks. And with practice, you begin to recognize, oh, this problem can be solved with this trick, that problem can be solved with that trick. And in this case, if I have a radical with an x inside of it and an x on the outside of it, U substitution will work a lot, not always, but it will work a lot. And we understand the trick. I let U equal everything inside the radical, 25 minus x squared. Du is then negative 2x dx. And I will actually point out, I do U substitution the way it was taught to me, which apparently is different than the way a lot of instructors do it now, or the way they learned. So as long as you can do U substitution, you are fine. I'm aware there are different ways to write this. I write it the way it was taught to me, which is the only way I can get it to work. So if this part looks a little bit different, that's completely fine, as long as you end up in the same place as I do. The way I do my U substitution, this is my U and my du. Now, I'm just going to rewrite all of this using u's and du's. I have a square root of 25 minus x squared, which is u to the 1/2. The stuff left over is x dx. I have to get that out of here. So I divide the negative 2 over. Those cancel. I get du over negative 2 is x dx. That accounts for everything else in this integral. X dx is du over negative 2. Now I just solved that. I'm aware, again, I can't even explain the other way this is done because it's not how I learned it, so my brain just doesn't like it. Now I just solve this. I pull the negative 1/2 out, and I get the integral of u to the 1/2 du, which is negative 1/2 u raised the power to that's 3/2, divide by 3/2, which is multiplying by 2/3, and then I put a plus c on there. Now I simplify this, the 2's cancel, and I get negative u over 3/2 over 3 plus c. And then I substitute back. U was 25 minus x squared, so I get negative 25 minus x squared to the 3/2 all over 3 plus c. And I'm done. And again, if you do your U substitution a little bit different, that's fine, as long as you arrive at this answer right here. But again, that's just one example of U substitution. My assumption is all of you know how to do U substitution. I will give you some problems to work on with it. If you are not, if you need more practice, feel free to let me know or stop by my office and I'll either work through problems with you or make a video going through problems or something like that. But all of this is the stuff you're already supposed to know. Once you get through U substitution, you then generally go to integration by parts. All of you know the formula, uv minus the integral of v du. And if you use different letters, I can't help you because that's the way it was taught to me and it's the only way I can remember it. So if I have some integral, the integral of x sine x dx. And we look at that and we say, well, okay, let's see, wait a minute. That's clearly the product of two functions. And I cannot come up with a U substitution. U would have to be x here because it's inside the sine function. But then that would also be u, and I end up exactly where I started. And like I said, the ability to look at a problem like we did on the last one and say, oh, there's a radical with an x inside of it. That will be u, but when I take the derivative of x squared, I get 2x, which is on the outside, so u sub will work. Versus this one, where there is no u substitution that will work here. Then I apply integration by parts. And again, we know the formula. I need a u and a dv. There's different ways to set these things up. If nothing else, you can do trial and error until you get one that works. Generally speaking, the easier function that will go away, you want the polynomial function usually, you want to be your u, because you can make it go away by taking derivatives. dv will be the other part. So here, I'll let u be x, dv is sine x dx. Now I differentiate and integrate. Derivative of u du is dx, antiderivative of v, antiderivative of sine is negative cos x. Now I have all of that, I plug it into that formula. And we'll just go over here. That becomes u, which is x, v, which is negative cos x, minus the integral of v, which is negative, so when I pull it out that becomes positive, cos x du, which is dx. And now this integral is one I can solve. So I get negative x cos x plus the antiderivative of cosine is sine. Sine x plus c. So again, I don't want to spend a lot of time doing examples of u sub in or integration by parts. If you need more practice, let me know, but you should all be familiar with these two things right here, because we will be using them in this class, and we'll just be incorporating them into more complex problems. A couple of other things that you cover in Calculus 1. The things I mentioned in the last video, revolutions of solids in cross-sectional areas. So suppose I have f of x equals x squared as x goes from 0 to 1. So if I graph it, I just get the parabola like this going from 0 to 1. In the last video, we found the area under the curve. Now I want to take this curve and revolve it around the axis, and I end up getting that. It looks like a top or something. And again, recognize that's three-dimensional. It's spinning around like that, so it's not flat. And the problem is that my integral formula, that's an area. It's length times width, which means that that formula cannot find that volume. But we said last time, an integral is not an area under a curve. An integral is a limit of a Riemann sum. And if I can find a way to maybe, in this case, geometrically find some geometric shape that will approximate this volume, because it's three-dimensional, then I can have a sum, which I can then take the limit of. I'll have the limit of a Riemann sum, which will then become an integral, blah, 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 blah. And I'm assuming you went over this, maybe even if it was only briefly at the end of Calc 1, which is why I'm doing this. But what we can use is cylinders. So again, it's a little bit hard to see, but if I go around there, and just like I did with my rectangles, now I have this cylinder, which approximates this part of the volume. Now here, I'll use a bigger cylinder, and maybe do that. I know that's a little bit hard to see, but if I stack these two cylinders, hey, I'll stack another one maybe right here. If I find the volume of each of those cylinders, the sum of those three volumes will approximate the volume of that solid. And then, if I want to make my approximation better, I'll just make these cylinders narrower. And by narrower here, because it's 3 dimensions, I mean I'll make their height get smaller. Because then they'll be narrower I'll have more of them, and my approximation will get better. And then how will I make that approximation better? I'll make them even narrower. I'll have more cylinders, add all of those up, and my approximation gets better. And ultimately, I have a summation of a bunch of cylinders, and I take the limit as the magnitude of the partition approaches 0, as the magnitude of those cylinders approaches 0, which means I have a bigger partition, more and more cylinders getting added up. And that should become, well, it's the limit of a Riemann sum, which I can then write as an integral. The only question is, what am I adding up? Before, I was adding up rectangles, so I had length times width, f of x times delta x. Here I'm adding up cylinders. The volume of a cylinder was equal to pi r squared height. So that's what I add up here, pi r squared height. Now, I just incorporate that. The radius, if I pick any of these cylinders, the radius of that cylinder is the function value. So my radius can be replaced with f of x, or f of x sub I, since this is done for all of them. So that's pi r squared. Height, the height of my cylinder is this distance, which we just said is the thing I'm going to shrink down. That's the thing that's going to change. That's my delta x, or delta xi. And now I have the limit of the sum of pi r squared height, the limit of the sum of a bunch of cylinders, which I can then write as an integral. The integral of pi f of x squared dx, pi r squared height. Keep in mind, this is f of x squared, the radius squared, not f of x squared. The square is outside the f of x. But now my formula for the integral has changed, but the method of solution is the same. I still just plug into it. And again, you should have seen this at the end of Calc 1, but a lot of times you don't have much time at the end of the semester, so you only go over this briefly. So I want to make sure you can do this. You will more than likely see this on exams and stuff, because I want to make sure it's clear. Okay, good. If it is clear, that just means your first exam will be really easy, because you already know this stuff. Okay, so suppose I have that one. I take the integral. The x's go from 0 to 1 of pi times the function, which in this case is x squared, my radius, squared dx, which is pi, it's a constant, so it gets pulled out, the integral from 0 to 1 of x to the 4th dx, which is pi x to the 5th over 5, evaluated from 1 to 0, which is 1 to the 5th, 1 pi over 5. And then when I plug in 0, I get 0. And I'm done. And now I can use my idea of an integral to get the area under a curve, the area between curves, and the volume of a solid of revolution. But you all understand how this works mathematically. I find the area under a curve, we did it in the last video, then I find the areas between two curves. If I can find the volume of a solid of revolution, then I can find the volume between two functions of the resulting solid. Meaning, suppose I have the exact same thing. We'll use x squared from 0 to 1. Then we'll also use y equals x, the line. That's a terrible line, but pretend it's actually straight. I want to find the volume of the solid between them. So now, if I revolve this, that's somewhat terrible. My shape will look like that, but keep in mind, this is revolving. So if you will, it looks almost like a cone, but a cone with a whole bunch of the inside stuff kind of cut out of it. So it's a cone with the big stuff missing on the inside. find the volume of that shape. But the principle here is the same as the principle of the area between two curves. Outer area, higher function value, minus inner area, lower function value. Top function minus bottom function. Outside function minus inside function. And then I can immediately set up my integral. The integral from 0 to 1, the outer function is pi, f of x is x squared dx, minus the integral from 0 to 1 of the inner function. Pi times the inner function is x squared dx. But then algebraically, to save myself some work, those are both integrals from 0 to 1 dx. They both have a pi. So I can write this as what difference of integrals is the integral of the difference. The integral from 0 to 1 of pi times x squared minus x to the 4th dx. And this is where some of the formulas you probably saw when you went over these, the disk method, the washer method, and all of that, this is where they come from. But as long as you think about it algebraically, add up cylinders. What's the volume of a cylinder? Rewrite that as an integral. Now I do outer cylinder minus inner cylinder. Oh, algebraically you can rewrite this. Then you don't necessarily have to memorize the formulas, which I had trouble with as a student. You can just derive these formulas pretty easily. And then, of course, this integral becomes pi times x cubed over 3 minus x to the 5th over 5, evaluated from 1 to 0, which is pi times 1/3 minus 1/5. The zeros don't matter. 1/3 is 5/15, 1/5 is 3/15, 5/15 minus 3/15 is 2/15. So you get 2 pi over 15, and you're done. And again, from here you can kind of mess around with this. What if I have functions that cross each other, like when I do the areas between two curves? Then I'll have to do several of these revolutions of solids. Same trick, just applied over and over. That's what we do a lot in calculus and in math in general. We use the same trick applied in different ways on different problems. The last thing in this video, which frankly, I do not know if you went over in Calc 1 or not. I think sometimes instructors do and sometimes they don't. Is cross-sectional or areas by way of cross-sections. And the idea is, this is a little bit harder for me to graph for you to see, but hopefully you can visualize things better than I can. We'll use the same y equals x squared from 0 to 1. Now, this is flat. Suppose at every point along the function, projecting out of the board, like I said, this is flat, the floor, if you will. Projecting out of the board is a geometric shape. In this case, we'll say a square. And these would actually overlap, but to make this easier to see, here I'll overlap. But making it easier to see by kind of spacing them out. So, if it helps, I have a couple of these that I 3D printed. And if it would help you to visualize these, feel free to stop by my office and you can look at these. Sometimes for me it helps to see them. And I'll hold these up to the screen so you can see them. This is my curve. So say this is y equals x squared right here. This is flat in the xy plane. That's why it's marked like this. So if I actually sketched this out on a piece of paper, there's my curve. But then at every point along the curve, I get a square. Here I get small squares because the function value is small. So from here to here to here is a square. At the end where it's at its biggest, I get a big square. Same idea here. This is the same curve, y equals x squared. Now my cross sections are triangles, where at every point along the function, I get a triangle. And it's easiest to see on the end, where here, where the function value is biggest, say this is 1, 1. I know all of this is reversed because I'm holding it backwards. If this is 1, 1, the resulting triangle projecting out of the board is at its biggest. Here, at other points on the curve, they're smaller. Here, for this one, your cross sections are actually semicircles. So like I said, I have these in my office. When this class is seated, I bring them to class so that students can kind of see them and mess around with them because it sometimes helps to visualize them. If you'd like to stop by my office and look at those, you can. Just let me know or just stop by. I'm here all the time. And you can look at them. But the idea is, once again, thinking about those things right there, they're three-dimensional, which means I'm looking for volume. How do I do that? When I was looking for the volume of the revolution, I used cylinders. Here, in middle school at some point, you probably learned about prisms. I can use prisms. Here, I can use a few square prisms where, again, this is hard to see, but say this square prism I would make extend over to here to approximate the volume in this part. I would take another square prism and approximate this volume. I would take a different square prism to approximate this part. Then I could add up those square prisms and approximate the volume. How would I make my approximation better? I'd make my square prisms narrower, like I did with the cylinders. And then how would I make my second approximation better? I'd make those square prisms even narrower. And ultimately, I would make them narrower, their height, like with the cylinder, smaller. And as they get narrower and narrower and narrower, and essentially almost become flat squares, that approximation for the volume will become exact. Which means, once again, I have the limit as the magnitude of the partition approaches 0 of the sum I equals 1 to n of something. And just like with the volume of the solid of revolution, I just need to figure out what that is. And in this case for cross sections, every single one will be different because it's entirely based on what prism you have. For this, it's a square prism. So, well, let's see. What is the formula for a square prism? The volume. It's the area of the base shape, but the base is a square. This is the function value, so that's f of x, times the width, but it's a square, so that's the same as the function value, which is also f of x. Then I have the height of the square prism, which we just said is the thing that I'm going to keep shrinking down to make this get better. So that will be my delta x. And these should technically be f of x sub I, because this is the approximation. But now, that's the volume of a square prism. If you remember again from middle school, the volume of a prism is base times height. That's the area of the base shape. This is the height, which is my delta x. Since the base shape is a square, it's just s squared. Length times width, because they're the same. Which is what I got here, f of x squared. That then tells me this will become the integral from 0 to 1, because that's the length I'm going with, of f of x squared dx. Solving that is easy. Plug in x squared, which is identical except with no pi to the cylinder. But to make sure we're clear on this, what if my cross sections were not squares? I'll just draw this a little bit right here. What if they were isosceles right triangles? Well, then I just have triangular prisms. The volume formula is still the same. That is still going to be my delta x. Now the base shape is an isosceles right triangle. The area is 1/2 base height. And in this case, because it's an isosceles right triangle, those are the same. So it's 1/2 base squared. If these were not isosceles, you'd have to do something different. This formula would change. There'd be a different geometric relationship. But then that means for this one, it would be the integral 0 to 1 of the function f of x squared times a half dx. 1/2 base times height squared dx, because base and height are the same. And these, if you think about it, make sense. How do I turn a square into an isosceles right triangle? I cut it in half. I cut along the diagonal. So it actually makes sense that this formula for square cross sections is the same as isosceles right triangle cross section, except there's a half here, because I cut them in half. Again, well, what if my cross sections were semicircles? I'm running out of room to draw all this, but if I have the same picture, where now my cross sections, I'll just draw one, are semicircles like that, well then what would my prism be? Circular prism, maybe? I don't know, circular base. It's actually a cylinder. But in this case, then my integral would be pi r squared height. The height, like before, is the thing that's changing. That's my dx. I have a pi here. It's circular. That makes sense. Now I actually have to be really careful based on how my problem is defined. The radius is not the function value. The radius is actually half of the function value, which means here my radius will be f of x over 2, all of that squared, pi r squared h. And then, of course, keep in mind, you'd have to square f of x, and you'd square the 2, and it would become a 4. I mention all of these things, 2 reasons. One, little details like this are the things that students tend to forget, even if they've seen it before in Calc 1. And if, like I said in the last video, and I will repeatedly say throughout this semester, if your assumption is the integral is the area under a curve, none of this will ever make any sense. If you understand that the integral is a limit of a Riemann sum, then for any geometric problem that we do, you can just say, what is the geometric thing that I'm looking at? How can I approximate it logically with a geometric thing? That will give you a formula. Once you have that formula, then you can set up a Riemann sum, take the limit, get an integral, and solve. Solving these integrals, I know I didn't solve any of them out, but solving all of these is essentially trivial. One power rule that you all know, and you're done and good to go. It's the setup that matters. The understanding of how do I create an integral, and how does that then give me what I'm looking for. The calculus part, the solving of the integral, that stuff is trivial and easy. I'm going to stop this video now because it's like really long and you have multiple ones of these to watch. This should cover the bulk of the review type stuff that we need. There's maybe one more thing separate from integrals that we'll need to review, but I might save that for later in the semester when we need it. Again, if there are other questions that you have that you think you'd like to review from Calc 1, or if you want more examples, or stop by my office, or if you want to look at those 3D printed objects I have, feel free to email me or stop by and let me know, and then we'll continue into Chapter 1 from there. I will point out, assuming you've made it through this entire video and you're still listening, even though to a certain extent all of this should be reviewed from Calc 1, you're going to see it on your exam. This plus the stuff from Chapter 1 that we're going to go over is all going to be incorporated into your first exam to make sure you're clear on it, because a lot of times, even if you maybe go over this right at the end of the semester in Calc 1, you don't necessarily get tested on it because you're almost out of time. So I want to make sure we're clear on how this works because it is important.